All right, let's go ahead and get started. I want to welcome you back to Unit 8. This is the mole. All right, folks, we've been talking about conversions involving atoms, and what we want to do now is kind of move our attention to molecules, combinations of atoms. So first we'll need to be able to determine the molar mass of a compound. It's not hard. The molar mass is the mass of 1 mole of molecules of a given compound. So to determine the molar mass, we simply add up the masses of the individual atoms which make up the molecules. For example, to determine the molar mass of CCl4, we simply add up the mass of 1 mole of carbon atoms, that's 12.01 grams, and 4 times that mass of, or the mass of 1 mole of chlorine. So for CCl4, we're going to add up carbon, which is 12.01 grams, got that right off the periodic table, plus 4 times the mass of 1 mole of chlorine atoms, or 4 times 35.45. That's equal to 141.8 grams. So I'll give you a minute then to calculate the total molar mass for carbon tetrachloride. Well, what would it be? All right, what we're going to do is we're just going to simply add up. So we've got the molar mass of the carbon tetrachloride is 12.01 grams and 141.8 grams for the 4 chlorines, right? And when we add those up, we get this number, 153.81 grams per mole of carbon tetrachloride. We now know the molar mass of carbon tetrachloride, and we can use that molar mass in calculations. All right, so let's take this example. It says how many moles of carbon tetrachloride are in 526 grams of CCl4. So I'm going to circle what I know, the 526 grams of carbon tetrachloride, and I'm going to underline what I'm looking for, moles of CCl4. So here's the solution. We're going to start with what you know and put it over 1. So I've been told that I've got 526 grams of CCl4. I'm going to put that number over 1 to hold the place. Hold the numerator and denominator firmly in place so I don't get them mixed up. And then what I'm going to do is whatever unit's on top, upper left, is going to go in the lower right. Grams of CCl4, grams of CCl4. And we've got moles of CCl4 on the top, right? Because that's what I'm looking for, isn't it? So 1 mole of carbon tetrachloride per 153.81 grams of CCl4, because that's what I've calculated. Remember, in that calculation I determined that 1 mole of CCl4 is 153.81 grams. So these two numbers are going to, or these two units, I'm sorry, are going to cancel away, and I'm left with moles of carbon tetrachloride. That's equal to 3.42 moles of CCl4, right? 3.42 moles of carbon tetrachloride. Okay, and that's it. That's my answer. All right. By the way, let's talk just a little bit about significant digits. How many significant digits do I have over here in the 526? Well, non-zero digits are always significant, so 3. How many over here? That's 5. So when I divide these two, I take the lesser of the two significant digits. I'm going to report 3.42. Let me go ahead and do that calculation, by the way, and follow me in this calculation to see what I get on the calculator. I get 526 divided by 153.81. And when I do that, the number I get actually on the calculator is 3.4198. Blah, blah, blah. The point is, I'm going to round it to 3.42 because I can only have 3 significant digits. That's my final answer. Folks, I really like this little schematic here because it talks to us about how to convert from atoms or molecules to moles and then to grams. Notice that moles is in the center. That's important, right? So moles is like the most important conversion unit, right? So if I want to go from atoms or molecules, I go through 6.02 times 10 to the 23rd. But if I want to go from moles to grams or vice versa, I have to go through using the atomic or molar mass, right? So we can use this chart then to help us to know how to do conversions, atoms to moles to grams, grams to moles to atoms. I can go both directions, right? So that's that. So from the above chart, we see that we can convert from atoms or molecules to grams through moles. And this chart is absolutely invaluable when you need to convert from atoms or molecules to moles to grams or back the other way. So let's be more specific now. If you want to go from atoms or molecules to moles, you're going to divide by 6.02 times 10 to the 23rd. But if you want to go the other way, if you want to go from moles to atoms or molecules, you're going to multiply by that same number, Avogadro's number. So moles to grams then is going to be, you're going to multiply by the atomic or the molar mass. If you want to go the other way, grams to moles, you're going to divide by the atomic or the molar mass. All right? Okay, so I hope that makes sense to everybody. Let's move on. All right, now that we're able to convert from mass in grams to moles to atoms or molecules, let's add another skill. We want to know how to determine something called percent composition. What do we mean by percent composition, or part of a whole? Right? That's what it means, part of the whole. Percent composition means part of the whole by mass, right? By mass. So let's take a look at this example. It says, what's the percent composition of nitrogen dioxide? What's the percent composition of nitrogen dioxide? Here's the formula for it, by the way. It's NO2, not hard. It's a covalently bonded compound with one nitrogen and two oxygens. So I want to know what the percent composition of each of the two elements that are involved is. Let's start with the nitrogen. So I, first of all, recognize that there's one nitrogen atom in the molecule, and that one atom has a mass of 14.01 AMU. Now, if I convert it to moles, it becomes 14.01 grams. So 1 times 14.01, of course, 14.01 grams, just like that. Now, if I'm concerned about oxygen, and I am, then I'm going to multiply 2 times 16.00. This time that's going to be 32.00 grams. When I add those up, I get a total of 46.01 grams. 46.01 grams. Now, how do I use that number to help me to determine the percent composition for nitrogen dioxide? Well, here's what I'm going to do. I'm going to take let's take the nitrogen first. Let me write N right here for nitrogen. So the percent composition for nitrogen is going to be this. It's going to be the mass of the nitrogen in grams, 14.01 grams, divided by the total, which is 46.01, times 100. So that's equal to 30.45%, right? That's if you divide 14.01 by 46.01, multiply that by 100, you get 30.45. Now let's do the oxygen. Now remember that it's NO2. So I have to multiply 2 times 16, so I get 32 on top, divided by 46.01 times 100, and I get this number, 69.55%. So that's it. The percent composition for nitrogen dioxide is that 30.45% of that molecule by mass is nitrogen, and 69.55 is oxygen. Now, if you want to do just a quick check, add these up, right? Because they have to add up to, if not 100%, there may be some rounding error, but they should be pretty close to 100%. This one's right on the money with 100% total, all right? So make sure that you check these when you're doing percent composition problem. All right, let's talk a little bit about something called empirical and molecular formulas now. What do we mean by empirical and molecular formula? Well, the molecular formula is the ratio of the atoms in a molecule. That's it. The ratio of the atoms in the molecule. It tells us nothing about the actual numbers of atoms. It just tells us the ratio of the atoms. So, for example, C2H2 is the molecular formula for a compound called ethane, right? So C2H2, I think. C2H6, I mean, is the molecular formula for a compound called ethane, right? So it tells us that there are 2 carbons for every 6 hydrogens in this molecule, right? Tell you what, let me draw that for you, please, if I could. This is what the Lewis structure would look like, just like this. We have 2 carbons and a hydrogen coming off of each one of those carbons, just like that, right? So that's ethane. That's the molecule. Now, that's the molecular formula. What about the empirical formula? Well, this is the lowest whole number ratio of elements in a compound, right? It's just the ratio, right? It's just the ratio. So, for C2H6, if that's the molecular formula, we could divide both the 2 and the 6 by 2, right? So if I divide by 2, I get CH3, right? CH3. So to determine the empirical formula for ethane, divide the subscripts by 2 and 6 by the lowest common multiple, in this case 2. The empirical formula for ethane then, which was C2H6, is this right here, CH3. All right? So that's empirical and molecular formulas, empirical and molecular formulas. Now, you could determine the molecular formula from the empirical formula if you know something, if you know the formula mass. Okay, now the formula mass is the same as the molar mass, right? Formula mass and molar mass is the same thing. So let's take a look at this example. It says the molar mass of butane is 58.14 grams. The empirical formula is C2H5. What is the molecular formula? We want to know the molecular formula. We know the empirical formula and we know the molar mass. We want to know the molecular formula. How would we do that? Well, the molar mass of the empirical formula is this. So if with C2H5, we've got 2 times carbon, its molar mass, which is 12.01, is 24.02. And for hydrogen, it's 5 times, well, 5 times, because there's 5 of them, 1.01, because that's the molar mass for hydrogen. So when I multiply those, I get this number. Now let me add these. 29.07 then is the molar mass for the empirical formula, right? For the empirical formula. Now we still don't know the molar mass, right? Or we still don't know the molar mass of the molecular formula, though. Remember that the empirical formula is the lowest whole number ratio, right? Which is C2H5. But they're telling me that the molar mass of the butane is 58.14 grams. So how are we going to handle this? It says, note that this is exactly 1/2 of the molar mass of the molecular formula. So the molecular formula is the empirical formula multiplied by 2. Again, this number right here is exactly half the molar mass of the molecular formula, the big one, right? 29.07 is exactly half of 58.14. That means that this C2H5 is going to have to be doubled. It's going to be C4H10, just like that, right? C4H10, and that is my molecular formula. Let's try another example. It says a compound contains 27.3 grams of carbon and 72.7 grams of oxygen. What is the empirical formula for this compound? What is the empirical formula for this compound? And here's the solution. Remember, the empirical formula is the simplest whole number ratio of the atoms in a molecule. Simplest. It's not necessarily the molecular formula, but it's the simplest whole number ratio. So the first step is to convert grams of carbon and oxygen to moles. So we've been given this in grams. We want to convert those to moles. So let's do that. We've got 27.3 grams of carbon over 1 times 1 mole per 12.0 grams. That's from the periodic table. When I do that division, I get this number, 2.27 moles of carbon, and this one right here, 72.7 divided by 16, we get 4.54. So now we've got it in mole. We got the two elements in moles. That's going to help a lot, right? That's going to help a lot. So now what we're going to do is the following. It says the ratio in moles of carbon to oxygen is 1 to 2. It's a 1 from going from here to here. Just multiply that number by 2, right? So it's a 1 to 2 ratio. 4.54 is twice as big as 2.27. So the empirical formula must be CO2, right? The empirical formula must be CO2. So again, we started with a certain number of grams of carbon and oxygen, and we've determined now what that formula is. The empirical formula is carbon dioxide. All right? Okay, let's move on. This is the third example. It says, analysis of a compound yields the following percent composition. We've got 6.64% lithium, 1.92% hydrogen, 29.8% phosphorus, and 61.6% oxygen. We want to calculate its empirical formula. Folks, I think this is a good place to end this one. I don't think we're going to be able to do justice in the remaining time. So let's go ahead and pause the video. We'll stop it right here and pick it up on the next one. I'll see you then. Thanks. Bye-bye.